Hello students, welcome to the introduction class of Database Management Systems. In this session we will learn what is a database management system, its applications, advantages, view of data, database languages, database engine, database users and administrators, and database architecture. Before understanding what is database, we will go through some terminologies. Data, the input given to the computer in the form of numbers, alphabets or any symbols etc., are called data. For example, typed content from keyboard, recorded audio, video, images etc. submitted to computer as stream of bits. Data arranged in an ordered manner to give proper meaning is called information. You can observe in the screen that the data that cannot give proper meaning is arranged in a proper manner in the table gives more information. Data stored in a computer storage that contains information relevant to some particular enterprise is called database. Give an example of a banking database. The branch table contains information of different branches of that bank. The account table contains information about each and every account of that bank. Branch name column of account table depends on branch table. Depositor table contains depositors and their accounts. Customer table contains basic details of each depositor. Database management system is a collection of interrelated organized data and a set of programs to access and modify these data. Database management system provides a convenient and efficient way to store and retrieve database information. Applications of database management systems. In banking, databases are used for storing and processing customer information, accounts, loans and banking information. In universities, database management systems help to store student information, course registrations, marks, grades, teachers' information etc. In telecommunications, database management systems are helpful for keeping records of calls made, generating monthly bills, maintaining balances on prepaid cards, and storing information about the communication networks. Human resources, for managing information about employees, their payroll, access and generation of paychecks. Airlines, this is the first area which use database in a geographically distributed manner. Databases are helpful for keeping plane routes, customer details and bookings. Credit card transactions, their authentication, billing are managed with the help of database management systems. Finance, in share market, keep track of bids and sale orders, execution of orders, holding of shares etc. are managed by database management systems. Sales, for customer product and purchase information, analysis of old sales data, database management systems are used. Researches, for analyzing observations of research data using warehouse. Hospitals, to manage patients' admission, medications, disease history etc. Manufacturing, for management of inventories, demand, supply and tracking production of items. Purpose of database management systems, or advantages of database management systems. Prior to database management systems, file processing system was used in which data was stored in operating system files. Application programs were developed which allow users to manipulate and add new information. The above conventional system has many disadvantages. Database management systems solved many of the issues in conventional file system. Data redundancy and inconsistencies. Difficulty in accessing data. Data isolation. Integrity problems. Atomicity problems. Concurrent access anomalies. Security problems. Data redundancy and inconsistencies. Software that uses file system is updated as the requirements arises. Different programs create the files and application programs as and when required. The files may contain some data in different files. This leads to more storage space and access is lost. This redundancy may also lead to inconsistency. When information in some file is changed, and the same information in another file is left unchanged. You can observe in the example that a data file in the file system is updated to a different new format. In conventional file system, both files coexist. This leads to data redundancy, that is duplicate data. If the content of the new file is updated, an old file is left unchanged, it leads to inconsistency. Difficulty in accessing data. The conventional file processing systems does not support accessing data in convenient and efficient manner. That is, subset of content of files cannot be retrieved. To select balance of a customer, Tarang, by his name, requires data from two tables. The data has to be fetched from both the tables. In order to fetch that data, we depend on the account number column from both the tables. This is a complex task in file system. It can be easily executed with the help of database queries. Data isolation. Since data is stored in file system uses different files and may be in different forms, writing application for retrieving this data may be difficult, where databases can accommodate for many types of data at one place. Integrity problems. Data values stored in the database must satisfy certain consistency constraints. These could not be enforced properly without a DBMS. For example, balance of certain bank accounts must not be less than certain minimum amount. This can be easily forced onto a column of a table. This cannot be forced onto flat file system. Atomicity problems. Computer system like any other device may subject to failure. It is crucial that database to be restored to the consistent state that existed prior to the failure. For example, consider 5,000 is to be transferred from Hrithvik's account to Tarang's account. This involves two transactions. First, 5,000 is subtracted from 28,000, and then 5,000 is added to 4,000. Somehow, if a system failure occurs in between the transaction before Tarang's account is credited, database goes to inconsistent state. To avoid inconsistency, transactions must be atomic. That is, either both credit and debit transactions should occur or neither should occur. Atomicity is difficult to enforce in the file processing system. Concurrent access anomalies. For the sake of overall performance and faster response, many systems allow multiple users to update the data simultaneously. If file processing system is used, concurrent updates may result in inconsistent data. Consider an example. Consider an account with balance 4,000. If two persons at different locations trying to deposit 8,000 and 5,000 respectively at same time to the same account, programs reading the balance at each terminal will read 4,000 from the account. First transaction will add 8,000 to the existing balance of 4,000 and update the balance as 12,000. Meanwhile, second transaction that had already fetched balance as 4,000 will add 5,000 to it and update balance as 9,000. As there were two transactions with 8,000 and 5,000 credit, we were expecting 17,000 as balance at the end of second transaction. Due to concurrent access, database ends with balance of 9,000 at the end of second transaction. Transaction Manager is a database management system component that will take care of such concurrent access in databases. But in conventional file systems, handling concurrent access is very complex and may not yield expected results. Security problems. Enforcing security in certain critical data such as banking is very difficult when file processing systems are used, because application programs are added as and when needed. You can observe from the below example, each and every account holder can have view-only access to their account details, and a manager can have view and edit access to all accounts. Enforcing such column or row level security is only possible in databases. View of data. A database system is a collection of interrelated data and a set of programs that allow users to access and modify these data. A major purpose of a database system is to provide users with an abstract view of the data. Following concepts of database management systems accomplish this task. Data models, relational data model, data abstraction, and instances and schemas. Data models. The data model is underlying the structure of a database. It is a collection of conceptual tools for describing data, data relationships, data semantics, and consistency constraints. There are a number of different data models that can be used to define a database. Relational model, entity relationship model, semi-structured data model, object-based data model. Relational model. The relational model uses a collection of tables to represent both data and the relationships among those data. Each table has multiple columns, and each column has a unique name. Tables are also known as relations. The relational model is an example of a record-based model. Record-based models are so named because the database is structured in fixed format records of several types. Each table contains records of a particular type. Each record type defines a fixed number of fields or attributes. The columns of the table correspond to the attributes of the record type. The relational data model is the most widely used data model, and a vast majority of current database systems are based on the relational model. Entity relationship model. The entity relationship data model uses a collection of basic objects, called entities, and relationships among these objects. An entity is a thing or object in the real world that is distinguishable from other objects. Semi-structured data model. The semi-structured data model permits the specification of data, where individual data items of the same type may have different sets of attributes. This is in contrast to the data models mentioned earlier, where every data item of a particular type must have the same set of attributes. JSON and extensible markup language are widely used semi-structured data representations. Object-based data model. Object-oriented programming has become the dominant software development methodology. This led initially to the development of a distinct object-oriented data model, but today the concept of objects is well integrated into relational databases. Standards exist to store objects in relational tables. Database systems allow procedures to be stored in the database system and executed by the database system. This can be seen as extending the relational model with notions of encapsulation, methods, and object identity. Data abstraction. For the system to be usable, it must retrieve data efficiently. The need for efficiency has led database system developers to use complex data structures to represent data in the database. Since many database system users are not computer trained, developers hide the complexity from users through several levels of data abstraction to simplify users' interactions with the system. Levels of data abstraction in database management systems are physical level, logical level, view level. Physical level. This is the lowest level of abstraction and describes how the data is actually stored. The physical level describes complex low-level structures in detail. Logical level of abstraction describes what data are stored in the database and what relationships exist among those data. The logical level describes the entire database in terms of a small number of relatively simple structures. Even though implementation of the simple structures at the logical level may involve complex physical level structures, the user of the logical level does not need to be aware of this complexity. This is referred to as physical data independence. Database administrators, who must decide what information to keep in the database, use the logical level of abstraction. View level. View level is the highest level of abstraction, describes only part of the entire database. Even though the logical level uses simpler structures, complexity remains because of the variety of information stored in a large database. Many users of the database system do not need all this information. Instead, they need to access only a part of the database. The view level of abstraction exists to simplify their interaction with the system. The system may provide many views for the same database. Instances and schemas. Schema. The overall design of the database is called the database schema. Below example schema specifies table names, relations between tables, column names, domain of each column. Database schema may contain more details than the one given in the example, however the example gives an idea. Instance. The collection of information stored in the database at a particular moment is called an instance of the database. Below is example of an instance. Instance contains snapshot of data at particular moment. Database languages. IBM developed original version of SQL in 1970. American National Standards Institute ANSI and the International Organization for Standardization ISO published an SQL standard in 1986. And since then, many updates are incorporated into SQL. Almost all relational database systems employ the structured query language. Although the name SQL refers query language, it can do much more than just query a database. Two major parts of SQL are DDL, Data Definition Language. It can define the structure of the data. DML, Data Definition Language, can modify data in the database. Specifying security constraints is also an important part of SQL language. DDL, Data Definition Language. DDL contains set of expressions to specify a database schema, storage structure and access methods. Creating table, defining keys, integrity constraints etc. are DDL expressions. Major properties of data defined by DDL are domain constraints, referential integrity, authorization. Domain constraints. A domain is a set of possible values that may be assigned to an attribute. For example, integer types, character types, datetime types. You can observe in the example account table each attribute is having some constraint. Declaring an attribute to be of a particular domain acts as a constraint on the values that it can take. Domain constraints are the most elementary form of integrity constraint. They are tested easily by the system whenever a new data item is entered into the database. Referential integrity ensures that a value that appears in one relation for a given set of attributes also appears in a certain set of attributes in another relation. For example, consider account and branch tables. Each account must be opened in any of the existing branches. In database language, branch name column of the account table must reference branch name column of branch. Each and every insert, update operations on account table, the referential integrity constraint refers to the branch name column of branch table. If at any time database modifications cause violations of referential integrity, the normal procedure is to reject the action that caused the violation. Authorization. All users of the database need not to be permitted to access complete database. These differentiations are expressed in terms of authorization, the most common being read authorization, which allows reading, but not modification, of data. Insert authorization, which allows insertion of new data, but not modification of existing data. Update authorization, which allows modification, but not deletion, of data. And delete authorization, which allows deletion of data. For example, a passbook printer has read authorization on transaction table. Each account holder can read row of his account only. Account creating clerk can have insert authorization. Cashier may have update authorization. Manager can have all these authorizations including deletion. Metadata. The output of the data definition language is placed in the data dictionary, which contains metadata. Metadata is data about data. The database system consults the data dictionary before reading or modifying actual data. The example shows probable data dictionary for account table, whose constraints are explained in the above table. The SQL data definition language. For creating account table using SQL, the query would be create table account. Account number, number of 10, primary key. Branch underscore name varchar 2 of 15. Balance number of 20,2. Check balance greater than or equal to 1000. This creates a table with name account. Account table will have 3 columns. Account number, branch name and balance. Account number column can store any number with maximum 10 digits, and it is also defined as primary key. Primary key means the values in the account number column must have a value, and no two accounts can have the same account number. Branch name column can have any value with 15 characters, and balance can have any number with maximum of 20 digits, out of which 2 digits are decimals, and the balance must be 1000 or more. DML. Data manipulation language is a language that enables users to access or manipulate data, as organized by the appropriate data model. Types of access DML statements do in database are: retrieval of information stored in the database, insertion of new information into the database, deletion of information from the database, modification of information stored in the database. DML are of two types. Procedural DMLs require a user to specify what data are needed and how to get those data. Example: PL SQL. Non-procedural DMLs, also termed as declarative DMLs, require a user to specify what data are needed without specifying how to get those data. Example: SQL. Declarative DMLs are usually easier to learn and use than our procedural DMLs. However, since a user does not have to specify how to get the data, the database system has to figure out an efficient means of accessing data. A query is a statement requesting the retrieval of information. The portion of a DML that involves information retrieval is called a query language. Although technically wrong, the terms query language and data manipulation language are used synonymously. The SQL data manipulation language. A query takes several tables as input and always returns a single table. Here is an example of an SQL select query. Select account number, balance, from account, where balance is less than 10,000. Here the query takes one table, account, as input, and gives output with two columns, account number and balance, with only rows specifying given criteria. Other important SQL queries in DML are: insert, inserts new row into table. Update, modifies content of a column value in the table for specified rows. Delete, deletes specified rows. We will learn all these queries in the SQL chapter. Database design. Database systems are designed to manage large bodies of information. They are part of the operation of some enterprise, where the database plays only a supporting role. Database design mainly involves the design of the database schema. The design of a complete database application environment that meets the needs of the enterprise being modeled requires attention to a broader set of issues. A high-level data model is the initial phase of database design. It provides the database designer a conceptual framework to specify the data requirements of the database users and structuring of the database to fulfill requirements. Data model translates these requirements into a conceptual schema of the database. The schema developed at this conceptual design phase will have description of the data and their relationships, provides a detailed overview of the enterprise. The designer maps the high-level conceptual schema onto the implementation data model of the database system in logical design phase. Physical features or system-specific database schema of the database are specified in physical design phase. Database engine. A database system is partitioned into modules that deal with each of the responsibilities of the overall system. The database structure in the image gives overview of the architecture of database, and the detailed architecture will be discussed in this video later. Three important modules of the database are Storage Manager, Query Processor, and Transaction Manager. Storage Manager. The Storage Manager translates the various DML statements submitted by application programs into low-level file system commands. The Storage Manager is responsible for storing, retrieving, and updating data in the database. The components of Storage Manager are: Authorization and Integrity Manager tests for the satisfaction of integrity constraints and checks the authority of users to access data. Transaction Manager ensures that the database remains in a consistent state despite system failures, and that concurrent transaction executions proceed without conflicts. File Manager manages the allocation of space on disk storage and the data structures used to represent information stored on disk. Buffer manager is responsible for fetching data from disk storage into main memory and deciding what data to cache in main memory. The buffer manager is a critical part of the database system, since it enables the database to handle data sizes that are much larger than the size of main memory. The storage manager implements several data structures at disk storage as part of the physical system implementation. Data files, which store the database itself. Data dictionary stores metadata about the structure of the database, in particular the schema of the database. Indices, which can provide fast access to data items. Like the index in this textbook, a database index provides pointers to those data items that hold a particular value. The query processor. The major components of query processor are DDL interpreter, interprets DDL statements and records the definitions in the data dictionary. DML compiler, which translates DML statements in a query language into an evaluation plan consisting of low-level instructions that the query evaluation engine understands. A query can usually be translated into any of a number of alternative evaluation plans that all give the same result. The DML compiler also performs query optimization, that is, it picks the lowest cost evaluation plan among the alternatives. Query evaluation engine executes low-level instructions generated by the DML compiler. Transaction manager. Often multiple operations on a database form single unit of transactions. But database has to execute them separately. System failure in between the transaction may lead database into inconsistent state. Similarly, databases are used for many online transaction systems. Billions of transactions happen in a banking database daily, so multiple people will be accessing database simultaneously. This is called concurrent execution. There is a possibility that concurrent transactions on same account may leave database inconsistent. In order to overcome such situations, Transaction Manager ensures ACID property for database transactions. ACID stands for atomicity, consistency, isolation, durability. Atomicity property of database ensures that all operations execute as single transaction and takes care of recovery if any failure happens in between. Consistency ensures that after the execution of a transaction, all values updated are as expected and correct. Isolation. Even though multiple transactions execute concurrently in the system, each transaction executes independently, and updates of one transaction does not affect other transaction. Durability. Even if the system failure happens in between a transaction, durability ensures that the database state is consistent. Ensuring the atomicity and durability properties is the responsibility of the recovery manager. If there is no system failure during transaction, the atomicity and durability are achieved. If a transaction could not complete due to any type of failure recovery component of the recovery manager detects the failure and try to complete the transaction. Otherwise, database will be restored to the state prior to the initiation of the transaction. And hence the atomicity and durability are achieved. As databases of enterprises are accessed by billions of end users, multiple users have to be allowed to interact with database concurrently. Transaction of one user should not affect the transaction of another user. This isolation property is ensured by Concurrency Control Manager, component of Transaction Manager. Concurrency Control Manager keeps interacting with the concurrent transactions to ensure the consistency of the database. Database users and administrators. People who work with a database can be categorized as database users or database administrators. Naive user. A person who doesn't know anything about computers and databases, but still uses database, are naive users. Many of us access banking database without knowing about it. Whenever we use online payments such as UPI transactions, ATM machines, money depositing machines, we will be accessing banking database. While shopping online, we might be updating order book of some merchant. A student checking his results online may be reading data from board or university databases. Naive users are unsophisticated users who interact with the system by using predefined user interfaces, such as web or mobile applications. The typical user interface for naive users is a forms interface, where the user can fill in appropriate fields of the form. Naive users may also view read reports generated from the database. Application programmers are computer professionals who write application programs. Application programmers can choose from many tools to develop user interfaces. Sophisticated users interact with the system without writing programs. Analysts submit queries to explore data in the database, or professionals using data analysis tools are sophisticated users. Database administrator. A person who has central control over the database system is called a database administrator. The functions of a DBA include schema definition. The DBA creates the original database schema by executing a set of data definition statements in the DDL. Storage structure and access method definition. The DBA specifies parameters pertaining to the physical organization of the data and the indices to be created. Schema and physical organization modification. To improve performance, or as the needs of the organization changes, the DBA carries out changes to the schema and physical organization. Granting of authorization for data access. By granting different types of authorization, the database administrator can regulate which parts of the database various users can access. Routine maintenance. Periodically backing up the database onto remote servers to prevent loss of data in case of disasters such as flooding. Ensuring that enough free disk space is available for normal operations and upgrading disk space as required. Monitoring jobs running on the database and ensuring that performance is not degraded by very expensive tasks submitted by some users. Till now we have studied different components of database architecture. Now let us look into an overview of the complete database structure. Naive users access database through interfaces provided. The interface communicates the application program object code to access or modify database to the query evaluation engine. Application programmers write application programs. Compiler and linker will generate an application program object code to access database. Sophisticated users use query tools or data analytics tools to query data in the form of DML queries. DML compiler and organizer submits these queries to query processor. Database administrators use administration tools to define or modify database schema in the form of DDL commands. DDL interpreter submits them to the query evaluation engine to create required data dictionary. Architecture of applications that use databases at backend. Database applications can be partitioned into 2 or 3 parts, termed as 2-tier and 3-tier architecture. Earlier generation database applications used a 2-tier architecture, where the application resides at the client machine and invokes database system functionality at the server machine through query language statements. Modern database applications use a 3-tier architecture, where the client machine is just a front end and does not contain any direct database calls. The front end communicates with an application server. The application server, in turn, communicates with the database system to access data. 3-tier applications provide better security as well as better performance than 2-tier applications. This completes the introduction of database management systems. In the upcoming sessions we will learn relational model, structured query language, entity relationship model, relational database design, and transaction manager. Thanks for watching.